All right, good evening, everyone. And it looks like our sound is working, so I'm going to start our screen share. And get started. Has everyone had a nice week to recover from the exam? It wasn't so bad, right? Good. No, overall, the class did quite well. It did have some challenging parts to it that really put your not just your ability to do everything that we had done in the class, but to apply it to some new situations. And so, but you, as a whole, handled it well. And you know by now, I guess, about the opportunity for a makeup exam. If you didn't do well on it, there are a few people who struggled. I am giving you a chance to improve your grade a little bit with this makeup exam that averages with your original exam. So my first priority is really learning out of this class, so it's done in a way to if you didn't do well on that, to allow you to do some extra studying, go through a new exam a couple of times, and hopefully have better command of the materials by the time you go into your second exam and the rest of the classes, and before you finish this course. So we're going to start on a pretty new variety of things now post-exam. It was really, before the exam, all about probability, about descriptive statistics, and related things, and some distributions. We're going to be applying all of this now in topics that are you're probably all going to use for years into the future if you continue doing any data analysis at all. You'll be using, for sure, descriptive statistics, and you'll want to know about distributions, but these are applications of these things into inference and hypothesis testing, which results in the p-value and the types of hypothesis tests that people expect you to do as a practicing biostatistician. And the basis for all of this is sampling variability. So I'm going to be starting today talking a little bit about samples and comparing those to populations. And I'm going to introduce the idea of sampling distributions. And this is something that is really a foreign concept to most people who come into this course. Even if you have taken statistics before, the idea of the sampling distribution is a little bit strange. And so I'm going to try really hard to give you some intuitive understanding of what they are and why they're important. And these will lead to the central limit theorem, which provides a basis for a lot of the hypothesis tests that we'll be using now and in the future, in particular the z-test and the t-test, as well as in the future analysis of variance. And then I'll end off just with a little bit about types of studies, experimental versus observational, and prospective versus retrospective studies. And I'm pulling today some things from chapters 1 and 4 in your textbook. Are there any questions about anything in the exam before I get started? Okay. So when I talk about a population, I am talking about every individual who we are interested in studying and who we are interested in making an inference about. So in this example, and we talked about this a little bit before, but a population could be everyone in the world, the entire population of the world, but it's often some subset. In this example, I'm talking about the population of Massachusetts, and I'm talking about the blood pressure in this population. So if we had unlimited resources, we might be able to measure the blood pressure of every individual in this population. You remember what it's called when you collect something about everyone in a population? It's a census. You don't usually get blood pressure, but you do get some things. And if you measure the blood pressure for everyone in the population, you could calculate the mean, and that would be an exact value. There would be very little uncertainty in it, maybe a little bit just in the measurement error, but by the time you averaged it among all of those people, there'd be very, very little uncertainty. So we would not have to talk about most likely uncertainty in this mean of the population if we actually had the resources to measure it on everybody. However, statistics is all about uncertainty and incomplete data, and what we normally work with, and you learn how to make inference from, our samples, because we can't, even with the little population of Massachusetts, we can't measure the blood pressure for everyone, so we end up measuring the blood pressure on samples. Samples are defined by the sampling strategy and the sample size. I'll be talking about sampling strategies in a little bit, but the most obvious aspect of a sample is how many people are in it. So this sample has a lot of people, this has fewer, this one has somewhere in between. And because it's an incomplete sample of the population, there's some randomness in anything that we calculate about it, because people are different. They're not all the same. So if we take the mean blood pressure in each of these samples, we're going to get slightly different answers in each of them. And that's just because of natural human variability and the fact that these are selected out of a population where there is variability. When you take something from those sample, and we'll be talking primarily about means in this course, and use that to try to say something about the population, that is what I'm going to refer to as inference in this course. When you infer something about the population from a sample. And what we will be doing is taking a sampling mean and inferring something about the population mean. We do a lot of inference on the means of samples. All of these individuals, in this case, would be our so-called study units or sampling units. And it is important to be able to define for a study, what are your study units? What are the units on which you make observations? So that mean is a group property, but the study unit is a property of the individuals in the population. And in this case, the study units are people, but in other instances, the study units could be schools, they could be school districts, they could be zip codes, they could be other units that contain any number of people. The study units could also be families, so there are various aggregations that could also be considered the study units, but they are the unit on which you make individual measurements. Our target population is the ideal population that we would like to describe. In this case, the population of Massachusetts. And the study population is the population from which we can actually sample. So it can potentially exclude some of our target population if there is some subset which we cannot sample, or which we sample at a lower probability than we think we are. These can lead to what is called selection bias, where the probability of some study units being sampled is different from the probability of others, and we don't know what that probability is. If you know what the probability is, then it's okay. There are ways to correct for it. But if you don't know, or the probability is 0 for some of the population, then that can lead to selection bias. There are some historical examples of selection bias, like studies that use phone calls to do surveys. And there was an example of one president. It was before my time. I don't know if, I think this might be one of Tony's example, but where a phone survey got the answer of who was going to be elected president terribly wrong, because it turned out that a lot of voters just didn't have telephones at the time. Yes?
Why in this example the study unit is not the blood pressure? Why it's not the people?
The study unit is the people. The unit of measurement, the measurement is the blood pressure. So, but the sampling unit is the person. And then finally, the sampling frame is just a list of all these units in the study population. So if you had a census that included the name and the address and the phone number of everyone in Massachusetts, that would make your sampling frame. And that is what then would allow you to take a random sample. Because from your sampling frame, you can use a random number generator or any one of the strategies that I'll talk about, and make a random selection of your sample, and then go and follow through and make your measurements of blood pressure on those randomly selected individuals. Recall that I'm using Greek letters for population parameters, like the population mean and standard deviation. These are mu and sigma. And the English alphabet, the Roman alphabet for sample statistics, like the mean and the standard deviation of the sample, for which I'm using X bar and S. So you can tell from the way that I write them down what I'm referring to. The classic sampling strategy, and probably still the most common one, is the simple random sample. And it's not always the best approach, but it is the simplest, and it is one that, if you can perform it, is free of bias, as long as you're actually able to perform this sample with. What makes it a simple random sample is that every individual in this population has an equal probability of being selected for the study. So I'm selecting here 3 groups, and well, let's just say I'm selecting individuals for the study and painting them blue, and they can just be anywhere in the population. So everyone has an equal probability of being sampled for the study. I go through with those equal probabilities and select a sample, and that defines who is going to be in the study. I actually made a mistake on the slide here. Can anyone tell me what the mistake is? This is systematic sampling. What systematic sampling is supposed to be is let's say for n equals 10, you select a number randomly between 1 and so I have 30 individuals here. So a number between 1 and what is this, 30 over 10? I'm just going to select a number between 1 and 10. I get 3. And then or let's see, if I've selected, so I'm going to randomly select, sorry, a number between 1 and 30. I select 2, and then just keep adding 3 to that until I've selected 1/3 of my population. So that's a systematic sample. The first, basically everyone is divided into, in this case, 3 groups, and then I randomly select one of those 3 groups. Yeah.
Is this considered randomness, complete randomness, because there's a pattern?
It's not complete randomness. It is a random, it's not a simple random sample, but it is a random sample because everyone in the population has an equal 1/3 probability of being sampled, and it is random. You have a 1/3, just like in the simple random sample case, everyone has a 1/3 probability of being sampled, but it's systematic. So so the method of selection is different.
I mean, because maybe there is a certain characteristic in people. Each 3 people, they may have certain characteristics. So when I make this selection, this systemic selection, so it's not.
So it depends on in the systematic sample. It all depends on how your sampling frame is ordered, right? So if you have your sampling frame ordered by last name, then you're going to have people from the same family next to each other, and you will be more likely to select if your average family size is, if all of your families are of size 2, then you'll be guaranteed never to select 2 people from the same family if they're all just couples. So there are, depending on how your sampling frame is ordered, there will be systematic effects of choosing this kind of sample, and you may or may not want that. But you're right; it's not a simple random sample. You're making a systematic decision about how you choose, but it still counts as a random sample. It only makes sense in certain scenarios. I'll give an example of where it might make sense. Oh, but what's wrong with my figure here? Yeah.
We are taking the blue as 2, then every 2 is 8, or it should be.
Yeah, that's right. Yeah, this is, I just somehow copied in the random sample again. So the ones that we're actually selecting, see if I can, so we're selecting 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, etc. Obviously, if these people had been sorted by whether they were boy, girl, or blue, then that would have had a systematic. There would be some systematic nature to our sample. Stratified sampling is an extremely useful and important sampling strategy. It's also sometimes called blocking. So what the stratifying means is that I first stratify my population according to some characteristic that I consider relevant to my study. So I'm actually dividing everyone here into blue, boy, and girl. And then I'm going to take a simple random sample from each of these strata. So if I'm selecting a 1/3 sample, I first select from, let's see, we have 10 of the blue figures. So I'm going to take 1/3 of that, and I'll round that to the nearest integer. It's 3 of them. So I will randomly select 3. I have to make a sampling frame of the blue people and randomly select 3 of them. And then I have another sample. There are 10 of each of these types of stick figures, and I'm going to randomly select 3 of each of them. So I'll end up with a sample of 9 if I do that. I could just select with 1/3 probability from each, and then the total sample size would not be fixed. But this is a very important strategy because it eliminates a source of random variability in my sampling. Because if the type of stick figure is important to my outcome, it reduces a source of variability in my sampling, which is the proportion of these 3 stick figure types. They will always have the same proportions in my samples. Even though that probability of being sampled is the same in all 3 of these cases that I've given. So it's still a probability of 1/3 of being selected. It's just that because of this stratification, I'm guaranteed that in my sample, I'll have the same proportions of each of these people types. Yep.
And where did the simple random sampling come in?
From each one of the strata, I take a simple random sample.
So being like the one that one.
Yeah, so I would take from this block, take a simple random sample of, let's say, n equals 3. And then from this one, I take and that's a simple random sample. And then from this block, I take another simple random sample of n equals 3. And from this block, I take one more.
And that just means every 3rd person.
Right, every 3rd person. Yep.
I want to know, in this case, the strata will have the same size?
Yeah.
Thank you.
Yeah, the key part of the stratified random sampling is that you are choosing the size of the sample from each of the strata. So in complex surveys such as the National Health and Nutrition Examination, the NHANES study, they will actually oversample or undersample some groups. So you don't have to, if there were 100 of these and 1,000 of these, you might not necessarily sample them in those same proportions of 10 times as many of the majority group. Because if you want to be able to make inference about these different subpopulations, then your power to make inference will depend on the size of your samples. So you may choose to oversample the underrepresented groups. And that is fine as far as, and there are advantages to doing that if you want to be able to make comparable inferences on each of these groups. Beyond a certain sample size, you don't necessarily need more people from a group. So So there are some real advantages to stratified sampling then. In a population of unbalanced subgroups, if you simply took a simple random sample, you would also end up with a very small sample of the smaller subgroups. Yes?
Yeah, my question is regarding this. If we oversample the small group, then we don't have a sample that is similar to the population.
Right. Yes, if you oversample one of your strata, then your sample is no longer representative of the population. And once you do that, you have to use a set of complex survey techniques for any estimation of prevalence or blood pressure that you want to do, in which instead of it just being, let's say, a simple mean, it's a weighted mean, where each observation is weighted by the number of people that they represent. Yeah, excellent point. Yes?
Can you please explain the last point, that it decreases the variance?
If the strata are well chosen, the sample variances are less than a simple random sample.
Is that good or bad?
That is a good thing, because sampling variance is your limiting factor in making inferences on the population. So let's say as an example, well, in this example, men and women have different average heights. So if we wanted to take an estimate of the population average height from a sample, there will be more sampling variability if the proportions of men and women in the sample are not controlled. Whereas if they are controlled, there will be less variability in your sampling. It only makes a difference for something like that, like heights, where it actually, there actually is a difference between those strata. Great questions. Any others? Okay, and finally, there is this thing called cluster sampling, which is done when you have some natural grouping of the individuals, in particular in a way that means that they need to be studied together. So a classic example could be, let's say, countries. We want to do a worldwide survey. However, it's not practical to send our study team to every single country in the world. So we, let's say, start by defining strata of countries that we think are somewhat similar according to, for the outcomes of our study, randomly selecting countries within those strata and only going to the subset of countries that are randomly selected, and then doing individual sampling within those countries. So one case where you do this is where there are units where it's only practical to visit some subset of the units. Another one might be is if there is an intervention that's going to be performed on a unit level. Let's say you want to look at the intervention or the effect of putting in vending machines in schools. And so everyone in a school is going to have access to the same vending machines. You can't study this just on individuals. It has to be studied at the school level. So if you were doing a case control intervention there, you would have to first randomly select schools. The ones that are selected, you do your intervention with the vending machine, and then you randomly select students within those schools. That's cluster random sampling. Oh, and I forgot to mention non-probability samples. By this, I mean samples where you have you have not controlled the probability of being sampled, and generally you don't know the probability of being sampled. So this happens when you make a call for volunteers and wait for volunteers to apply for a study. Patients who walk into a cancer clinic, you're not controlling the probability of who comes into this particular clinic, or other so-called samples of convenience, or convenience samples. The problem with these, because you don't know the probability of selection, is they are prone to selection bias, in that you will have some people that are highly probable to become a part of the study and some people who are not probable at all, and you don't know what those probabilities are. So sometimes you cannot avoid this, but it is prone to selection bias. So that's something to keep in mind. You will be hearing more about this, I think, over the course of your degrees, different studies, and about selection bias. You'll be getting taught to think about selection bias as a part of reading the literature and designing studies. Here's an example of geographic sampling, so something kind of different. But I have a map here with several archaeological sites. I can't read them on my screen here, but let's see. This is a historic homestead. We've got a river going through here. We've got some kind of a quarry. A historic wagon trail. So in this map, it's been divided into with an equal grid, so into equal little plots, and these certain known important sites are shown on the map. And here are our four different types of samples. So simple random sampling would just be randomly placing deciding which. So what's our sampling frame here first? What would the sampling frame look like? Yeah.
All of the individual boxes.
Yeah, all of the individual boxes. So if you were to write it down, it might look something like a spreadsheet where each of these boxes is given a number and an X position and a Y position. And then for the simple random sampling, you just select randomly from all of those. And if you did this, some of these, what's highlighted here, are the places where one of the observations has fallen on top of one of these known special sites, and the rest of them that are just hollow squares have just fallen somewhere else on the map. A systematic sample, which there might be reasons that you would want to do this, would be one where you start at a random position close to the beginning, and then you select this looks like every third spot here. It's actually less than a third overall. It's maybe 1/9. So this way, and this is sort of an example of maybe somewhere where it would make sense to take a systematic sample if you wanted to be sure with you're going to take that sample 10% of the sites, and you wanted to be sure to cover every part of the region, or at least not to have any large areas that don't get sampled, then a systematic sample might make sense. You can see there are some spots here that just randomly did not get anywhere chosen near them, and then others where there are some plots chosen right next to each other, and you avoid that with the systematic sample. So the stratified random sample, in this example here, I'm dividing the region into two areas, one above the river and one below the river. And then I'm taking simple random samples of predefined size from each of these regions. And by doing this, I am guaranteeing how many plots get taken above the river and below the river. So that's one type of sampling variation that's been removed from our study design. There will be no variability in how many are above or below the river. In non-probability sampling, there are any number of ways you could do it. Maybe you just decide that you think this historic wagon trail is important and this historic homestead are important, so you put all of your samples there. And you don't know then what you might have missed in the other areas, but you're just choosing to put all of your resources into something that you think is important. And this would be a kind of close equivalent to a volunteer study with limited resources, where you just put out an email call or put something up on a website saying we need volunteers, waiting for people to come in and spending your time and your resources on performing the study with those volunteers. You don't really know what you've missed by doing that, but you know what you have. So, I have a little quiz for you. This is a data set. The Run 10 data set, it's included in R, and it is the finishing times for 16,924 runners in a 10-kilometer race. So for each one of them, we have the time that they took to complete the race, which varies from about the fastest time of about 40 minutes to the slowest time of about almost 180 minutes, or maybe more. There's even more up there. So first of all, is this a sample or a population? This isn't a trivial question, so it needs more than just a yes or no answer, yeah?
Technically, a population means every runner.
I think so. I would call it a population where the target population are the runners of this race. You know, you could think about it as a sample and think of this as a random sample of all 10K runners. Clearly, you would have some selection bias for this race, but you know, you could think about it potentially as a sample as well. But in terms of the runners in this race, it's the population. We have all of the finishing times. So I'm going to call this mean, which is somewhere just under 100 minutes. I'm going to call it the population mean. If I asked you this, you know, on a homework or test, I wouldn't grade you wrong for saying that this is a sample if you explained what your target population was and what the sampling strategy was. Because I think you could argue that it is a sample of something. Maybe it's a sample of all of the years over which this same race is run. If this is just 1 year out of 100 years that it has been run, and your target population is the entire history of runners of this race, future and past, then you could think of it as a sample as well. So there's no real right or wrong answer there, but you just have to think about what your target population is. Another tricky question for you. Here's that histogram of all 16,924 runners. And now I've randomly selected 100 runners, and I've plotted a histogram of them, of the completion times for 100 runners. So what is this 100 runners that I've randomly selected? What would you call that? It's a sample. Very good. It's a sample from our population, our target population of 16,924. Now, this histogram of running times, does it look similar to the population running times?
No.
To some extent.
Yeah, explain. So why do you say to some extent?
Because there is here from 70 to 80,
Yeah.
it's not similar to the population. It's larger than from 80 to 90, which is not the case in the population.
Yeah, there's a bit of a drop.
And there no in the 100 runners there is no no samples above 140, but in the population there are some runners. That's what I say. There's to some extent.
So to some extent, and how is it similar?
The other categories of the histogram, like it's decreasing by increasing the running time. The sample size is decreasing by increasing the running time. I mean, like it's to some extent bell-shaped.
Yeah, that's a very good point. It's to some extent bell-shaped. Yeah, that's a similarity. Did you have something to?
I was going to say that they're both generally normally distributed.
Yeah, they're both kind of normally distributed, bell-shaped. The middle is about the same, right? It's somewhere around 90, 100. And yes, as you pointed out, there are more extreme times in the 16,000 than there are in 100. You'd expect that, right? You're not going to catch, you're probably going to miss the very fastest and the very slowest people if you only randomly select 100 people. But most of them, so most of them here between 40 and 140, and most of them here between 40 and 142. Right? So that you are missing the extremes, but still most of the people are in about the same range. So the center of it is pretty close to the same, and the spread of the times is kind of the same. And there is some little glitches, like there being a little bit of a dip here. That's because it's a random sample, and in a small enough random sample, you'll see a fair bit of variation in your times. 100 is not so small. So, how many samples was this? How many samples did I take here? What's that? Just one, yeah. In the terminology I'm going to use, this is one sample of size n equals 100. It's one sample. The sample is, you choose your sampling strategy. In this case, it's a simple random sample. You choose the sample size. You take a sample of that size, and that's one sample. 100 runners here. So then what is a sampling distribution? A sampling distribution is the distribution of the statistic for many samples taken from that population. So we just took one sample. A sampling distribution is a property of that sample that you would observe if you took sample after sample after sample to make a distribution of samples. So for example, we take this sample, we calculate a sample statistic, let's say the mean, and you repeat. So you keep on taking random samples of 100, you calculate the mean every time, and then the distribution of those means is the sampling distribution. So the key point here is that the sampling distribution is a property of the samples. It's not a property of the individuals. Any questions about that distinction? It's a key distinction between a population distribution and a sampling distribution. Yep.
Just a question about, so you would plot these to see the variation between your samples, basically, and to see if, like, if the means were normally distributed? Or
Well, it would be nice if you could plot your sampling distribution, but how many samples do you normally have in a study, do you think,
not
in real
that
life?
many.
One.
Yeah.
You get one sample only.
So when do you do this?
So that's what is very unintuitive about this at first, is that we're going to do all kinds of things based on sampling distributions which you never observe. You only get your one sample in real life. However, all of the inference that we do is based on sampling distributions. That's why I say this is maybe a first, like, really unintuitive thing in this course, because it's a basis for most of what we do, but we never actually observe it. Importantly, sampling distributions are different than the population distributions. Very important. So if our population distribution looks something like this, so this is whatever, our serum cholesterol, our blood pressure. If our population distribution looks something like this, then our sampling distribution of the means, so you take samples from this population and calculate the means of the samples, that distribution is going to be narrower than the population distribution. Why do you think it's narrower? In, like, intuitive terms.
Sampling bias?
Hmm?
Bias, sampling bias?
No, not sampling bias. No, these are proper random samples. Yeah.
Because your sample is obviously smaller than a population, so you're going to have a more narrow range.
It's not quite it. Let's see. I want to get some more answers here. Yeah.
The mean value is almost similar, so if the distribution is around the mean.
The mean value is what?
Almost similar in both the population and the sampling distribution. So the population is around the mean, that's why it's the mean.
Yeah, so you're on the right track. The sample mean is going to be similar to the population mean. Any more insights? Yeah.
But the standard deviation is smaller and it's simple.
Yeah, the standard deviation is smaller. I mean, that's a description of what you're seeing here. But I want just an intuitive explanation of why this would be. Yeah.
You take small samples of the population over and over again, you'll eventually get a distribution that looks like the population, but if you only take a few of them, you're probably not going to get any of the outliers. So you probably get individual closer to the mean.
No, in this case, this sampling distribution is from a very large number of samples. Let's say this is from an infinite number of samples taken. Well, tell me something. In one case, we're talking about individual cholesterol levels in the population. In the other case, we're talking about the average population level of a group. So forget I've polluted your minds with graphs and formulas. Which do you think is going to be more variable? Individuals, right? The whatever it is, the serum cholesterol, the blood pressure, it's going to be more variable among individuals than if you average together like all the people in a class, because the outliers get mixed in with, if someone has very high blood pressure, they'll tend to get averaged with someone else with low blood pressure. The properties of groups are less variable than the properties of individuals. And this is a very general thing. Doesn't really matter what thing it is that we're measuring here. It's a very general thing that the properties of the average property of a group will be less variable than the individual observations. So, I mean, we could apply this to like the masses of planets. You know, the masses of planets are, you know, in our solar system varies from Pluto to Jupiter, or Pluto's not a planet anymore, I don't know. But, you know, there's a big variation. Whereas if you took instead the average masses of planets in solar systems the same size as our solar system, there's not going to be as much variability. They'll have some big ones, some small ones, but you average them together. Maybe I'm going a little far afield with this example. I have no idea about astronomy, but I'm assuming that that is true. Take something else like let's say that the age of individuals in the population. The age might vary from 1 day old to 110 years old. But if you really randomly select groups from the population, you know, the average is going to be somewhere in the middle there. You're not going to just randomly select all 100-year-olds or all infants unless there's some selection bias. So that average is not going to have as much variability as the individual ages. Very general property. So in this case, what I'm showing is a distribution of blood cholesterols and then the distribution of average blood cholesterols in samples. So let's say these are samples of n equals 30. If I were to keep on taking samples of n equals 30, thousands of times, millions of times, an infinite number of times, the variability of those averages that I would see would end up being quite a bit less than the variability of cholesterol in the population. But of course, if we're doing some study of blood pressure or serum cholesterol, we're likely to collect either one sample or to select one sample from our cases and one from our controls and have 2 samples. But that's all we're going to get. We're not going to have an infinite number of samples. So, question, is the histogram, these are the histograms that I showed you before, the running times of all 16,924 runners. Why does this look kind of different than it did before? What am I plotting different here?
Runner age.
Oh, sorry, yeah, it's age now, not completion time. So just to give you something different. So these are all 16,000 runner ages, and these are the ages of my sample of 100. The individual ages. So my question is this histogram on the right for these 100 runners, is this an approximation of the population distribution or of the sampling distribution of mean ages for 100 runners? This is going to test how well you really understood what I was just blathering to you about. Which?
Population distribution.
Let's see, put up your hand if you think it's an approximation of the population distribution. Got a few. Put up your hand if you think it's an approximation of the sampling distribution for the mean of samples of 100 runners. Got a few. Okay, I want a representative from each group now. Why do you think it is an approximation of a sampling distribution? No one wants to argue this point? Okay, how about the other one? Someone who thinks that it's an approximation of the population distribution. Why do you think that?
To some extent, the same variability as the population.
Yeah, I mean, just empirically, it looks kind of the same as the population distribution, just looking at this histogram. That's a good reason. Any others?
Say that it's 100 runners, so in sampling distribution, wouldn't it be sampling 100 people at a time?
Yeah. So yes, we have the empirical argument, then we have the sampling argument, that in order to observe the sampling distribution, you would have to take samples of 100 runners over and over and calculate their mean ages. Whereas this is just one sample of n equals 100 and showing their individual ages. So because it's a histogram of individual ages, it's an imperfect approximation of the population distribution. And this mean of 35 is just 1 point on the sampling distribution. You would need to repeat this an infinite number of times to get the complete, exact sampling distribution. It's just 1 point. So if we only get to see 1 point on the sampling distribution, what's the point of a sampling distribution then? Well, this brings us to the central limit theorem, which is, as the name implies, it's important. It also implies that it is about the central tendency of a sampling distribution. Why it's important to us is that the central limit theorem is going to allow you to calculate some properties of the sampling distribution even though you can't observe it directly. Because it relates the sampling distribution of means to the population distribution for large samples. So, 3 points to the central limit theorem. The first is that the mean of the population and the mean of the sampling distribution are identical. Again, this only holds for either normally distributed data or for large samples. For large samples, it turns out it doesn't matter what the population distribution is. So number one was that the means of the population and the sampling distribution are identical. Number two is that the standard deviation of the population is related to the standard deviation of the sampling distribution of the means by this formula. SE stands for standard error. The standard error is the standard deviation of the sampling distribution, and it is equal to the population standard deviation divided by the square root of n. So, we now have formulas for the mean and the standard deviation of the sampling distribution if you know what they are from the population, for the population distribution. And then third, for large n, large samples, the shape of the sampling distribution of means becomes normal. And this is really neat. It's saying that it does not matter what the distribution of what you're measuring in the population is. If you have a large n, your sampling distribution will be normal. So for large n, we now know everything. If you know the mean and the standard deviation of the population, then you know everything about the sampling distribution. You know its mean and its standard deviation, and you know that it's normal. So those are the 3 points of the central limit theorem. And these are a couple of examples. Here is a uniformly distributed population measurement. So all equal probabilities between these bounds. with n equals 1. So this means just taking individuals and measuring some property. If you take instead samples of n equals 4 and calculate the means and do this repeatedly, it's already looking pretty normal. N equals 7, it's looking normal with less variance, because remember the sampling standard deviation is the population standard deviation over the square root of n. And with n equals 10, it's looking quite normal and with even lower standard deviation because that denominator, the square root of n, is larger.
Sorry, you said it's the standard deviation of the population over 1 minus square root of what?
Population standard deviation divided by the square root of n being the sample size. Yeah.
So basically, if you take an infinite amount of samples from a population, you'll get a perfectly bell-shaped curve.
Nope. If you take large samples, if n is only 3, then you're not guaranteed that it will be a bell curve. If n is, let's say, greater than 30, then you will get that bell curve. Yeah, and it depends on how non-normal the population is. So with this uniform distribution, it gets bell-shaped normal pretty quickly, even for n equals 10. If you have some extreme skew, then you need larger sample sizes for the sampling distribution to look normal. So in this case here, this is the ages. I'm actually doing a simulation. I'm taking sampling size here. Well, here's n equals 1. So this is just repeating mirroring the population distribution. N equals 1. For n equals 10, you see less of a skew, and you see it getting squashed. It's narrower. For n equals 25, there's no skew at all, hardly anymore. It's even narrower. For n equals 100, even narrower. And n equals 1,000, very, very narrow, no skew. So by the time you take samples of size n equals 1,000, there's very little variation in the average age of these random samples. All of that individual variation has been averaged out in these big groups of n equals 1,000. So both of these kind of show you these key points of the central limit theorem, in that the central tendency, the mean, is the same, but the standard deviation gets narrower and the distribution becomes more normal as you take larger samples. And all of these are some fairly large number of samples that are taken in this simulation. So, for a random sample of size n from a population of mean mu and standard deviation sigma, the sampling distribution, that is the distribution of the mean values of the samples, is normally distributed with a standard deviation that we call the standard error, that is equal to sigma over the square root of n. That's the standard error. So when you hear the words standard error, that is always referring to the sampling distribution. It's referring to the standard deviation of the sampling distribution. There's a lot of confusion sometimes over, I hear questions like, well, should I report the standard deviation or the standard error from my sample? And I've heard justifications like, well, maybe I'll report the standard error because it's smaller, it looks better. Well, they're different things. The standard deviation is an estimate of the population standard deviation. The standard error is an estimate of the variability of your sampling distribution. They're just different things. They have different uses, different interpretations, everything. And it tells us how much variability you would, so you just have this one sample mean, but it tells you how much variability you would expect in that just by chance due to the fact that you're taking a random sample from the population. And this sampling variability again decreases with larger sample sizes, which means that the sample means will tend to fall closer to the population mean with larger samples. These are all for simple random sample. Of course, for a stratified random sample, then the sampling variation might actually be less than this. So that third point, that the sampling distribution is normal for a large sample. What's a large sample? Well, it depends on the population distribution. Something that's already close to normal, even n equals 5, will have a normal sampling distribution. For a very skewed distribution, you need a larger sample. But in practice, large N can even just be about 30. By the time you're at n equals 30, no matter what your population distribution is, your sampling distribution is going to look pretty normal. For proportion, so if we're just talking about the fraction of times that heads comes up in a coin flip, or the fraction of public health students in the population, for any kind of proportion, it turns out that for large N, again, the sampling distribution of those proportions is approximately normal as well, with a slightly different formula for the standard error. So the number that we're talking about is the proportion on a binary variable, and the standard error is given by this square root of the proportion times 1 minus the proportion over n. So with proportions, the sampling distribution is again approximately normal. You just need a different formula for estimating the standard error. But other than that, you can then treat it like a normal sampling distribution for large sample sizes. So what is the use of the central limit theorem, and what is the use of sampling distributions anyways if we don't actually get to observe the sampling distribution? Well, it allows us to do inference about the population from our sample. If we have a large N, then we can calculate this particular formula about sample means. So you take your mean minus your mean of the population divided by this standard error and get a value z. You'll just have one observation or one value of that z if you've taken one sample, but you'll know that your distribution is normal with mean 0 and standard deviation 1 because you've subtracted the mean and divided by the standard error. So now your sampling distribution of this value z is the standard normal distribution, the one with mean 0 and standard deviation 1. So if sigma is known from the population, I'm not going to put or estimated. I'm just going to put if sigma is known, we'll get to whether if it's estimated later. You can calculate z for your sample, and then infer whether that sample came from a known or theoretical population of mean mu. So what does that look like? Well, first, you can also get confidence intervals on that because you know the distribution of this z, and you remember from what we did about the normal distribution that you have 95% probability of it falling between minus 1.96 and 1.96. That was from the empirical rule. So just by plugging in those minus 1.96 and 1.96, along with what we've observed for x bar and what we know for sigma, you can get an upper and a lower bound on mu. And you'll get some practice with that as soon as I'm done talking here. But the key thing that I want to say here is that if you know theoretically what z is, or based on an assumption about the population, so you assume that in the population the mean serum cholesterol is, I don't know, 200, then from the central limit theorem, you can estimate what your sampling distribution would be, and from the value of z that you observe, calculate how probable that is to have actually come from that sampling distribution. And the key thing is if it's unlikely that the particular value of z that you observed in that sample is a part of this theoretical sampling distribution, then you're going to reject what we'll call the null hypothesis. We'll get to that next class, but which would be that your observed sample is a part of this assumed or hypothesized sampling distribution. This forms the basis not only for the z-test, but for t-test, ANOVA, confidence intervals, all kinds of things. And it tells us the sampling distribution for any population as long as our sample is large enough, as in something around or greater than 30, even if you don't know the population distribution. So you have to have some kind of an assumption or knowledge about the mean in the population, but you don't need to know the whole distribution, just that mean. And our basis for inference will be calculating the probability that our sample came from a sampling distribution that you would expect theoretically from this population. Okay, and I'm going to wrap up just by distinguishing what we're talking about when we say experimental and observational studies. The key thing in experimental studies is that there is an intervention. So an important type of experiment in public health is the randomized controlled trial, where your sampling frame are randomized into a, let's say, a control and an intervention. And there's an intervention because people are randomly selected and assigned to one of these groups or something differently is done to those two groups. So it's experimental because you randomly select groups and you do an intervention. So you know what the probability of receiving that intervention is among your study sample. And these are the only way in public health to absolutely prove causality. Because if you have randomly assigned your study participants to these groups, you know that there can be no confounding or other factors about those individuals that is actually causing what you observe, because they all have the exact same probability of receiving your intervention. So just because a study takes place in a clinic, if you're comparing the people who responded positively to a cancer treatment to those who did not respond positively to the cancer treatment, that doesn't make it an experimental study. Even if you go and do experiments on biological specimens, if there's no intervention, no randomized intervention, it's not an experiment. So if it's the case that all of the patients are receiving the same standard of care, and then you do experiments that are just comparing those who responded favorably and unfavorably to treatment, that's not an experimental study. And I sort of highlight that point because it's a common cause of confusion. Just because it's taking place in a clinic and it sounds scientific doesn't make it an experimental study. Everything else where there's no intervention is an observational study. So if you are, in that example, just observing something about these groups of patients, one who responded and one who did not, or you're taking a random sample from the population and giving them a questionnaire, or let's say, even if there isn't some intervention there, like giving a questionnaire, you could consider an intervention. Giving them some product and seeing what they think about it. It's observational because that intervention was not randomized. So unless you randomly assign an intervention group and a non-intervention group where you make your comparison, then it's an observational study. Oops. And lots of important studies are observational studies. So it doesn't mean that they're useless, it just means that they're not experimental. So the New York City Haynes, the National Haynes, Behavioral Risk Factor Surveillance System, these are all cross-sectional observational studies because they take a cross-section of the population. Some of them take blood, take other vital measurements, they do all kinds of things, scientific things, they give questionnaires, collect data on a random sample of the population. They're observational studies. And they're cross-sectional observational studies because they're all taken at one point in time. Retrospective observational study would be where you actually recruit subjects based on something like health status. So you take a group of people who have had cancer and a group of people who have never had cancer. That makes it a retrospective study. So whereas in a cross-sectional study, you're just picking people randomly from the population. In a retrospective study, you're picking them based on some outcome of interest to compare them. And a prospective study is one where you pick a cohort and you follow them through time, like the Nurses' Health Study. And I'm sure I don't really need to hammer this in because I'm sure you're getting it in your epi class and you'll get it more, but you can't prove causality from observational studies. You can infer causality, you can do a lot of work to try to make it improbable that there's, if you're trying to If you're interested in the relationship between smoking and lung cancer, you cannot prove causality there without doing an experiment, but through enough different types of inference, you may get to a point where you consider it unlikely that, that there is not a causal relationship between smoking and lung cancer, or between atmospheric carbon dioxide emissions and global warming. You can't prove causality without actually doing experiments on the atmosphere, but you can build up inference and models that lead you to believe that it's very likely that there's a causal relationship. So in that example, does smoking cause lung cancer? Experimental approaches, if you really wanted to prove this, you could design a study like this where you take people who have never smoked and assign them randomly to smoking and non-smoking groups. The smoking groups, you force them to smoke, and the non-smoking groups, you make sure they don't smoke, and then follow them for years to see who develops more lung cancer. Obviously, you can't do that, not on people anyways, and so this is, while it would prove causality, not something you could do. Alternatively, you could take smokers and assign them either to a no intervention group or to a cessation program, and as long as that cessation program has some effectiveness, then looking at the overall rates of lung cancer in those groups, not just comparing those who quit and those who didn't in the cessation program, but at the level of where the intervention was occurred, like those who received the cessation program and those who didn't. That would be another way to prove causality. And just as a little bit of a side note here, in a case where you have an actual experimental random variable like a cessation program, which you're able to assign randomly, but that you know that on its own, a cessation program does not prevent lung cancer. Just theoretically, we know that like handing some educational materials and yelling at people and saying don't smoke, that on itself cannot prevent lung cancer. Its only plausible mechanism of answer would be through the actual cessation of smoking. In that case, the cessation program is what's called an instrument, and this is an instrumental variables analysis, which you'll learn about in your upper level epi classes. But it is another way to infer causality in a case where you have an instrumental variable like applying a cessation program, which does not in itself cause the outcome that you're interested in, but it does through a causal pathway. A few observational approaches. One would be the cross-sectional one, where you take a sample of the population, ask them whether or not they've ever been diagnosed with lung cancer, and how much they smoked. And if you see a higher rate of lung cancer among those who smoke, then you might infer that smoking causes lung cancer, but it's possible that it's just that the smokers also have higher levels of some other exposure that causes cancer. And you can try to control for things like that, but you'll probably never be able to rule out all of the differences between these groups that may be causes of lung cancer. The retrospective approach would be to recruit 50 cases with lung cancer and 50 without lung cancer and see which group smokes more. And this would be more efficient because lung cancer doesn't have that high a prevalence in the population. So here we get to survey only 100 people, and it would take a lot more if you're doing a cross-sectional study. But it has the same issues with potential confounding by some other cause of lung cancer as the cross-sectional study. And the prospective approach would be to take a group of smokers and a group of non-smokers and follow them over the years and see which develops lung cancer more frequently. Again, the same kinds of issues, that there may be other systematic differences between these groups of smokers and non-smokers. So when you can only have observational approaches, evidence really has to accumulate over a variety of different populations and different approaches. And when you see the same answer consistently enough, you start to believe that it's probably causal. Or maybe you don't, maybe you see inconsistent results in different populations. So just to wrap up, you should know now what a sampling distribution is and how it relates to a population distribution through the central limit theorem. And know these general classes of studies, experimental and observational studies. And I didn't write it down here, but you should know the different strategies to random sampling that I mentioned in the beginning. Are there any questions before I give my throat a break and we take a little bit of a break and go over to the lab? All right, thank you.
About 10 minutes.